What happens when a massive ship suddenly loses propulsion while enormous waves are already attacking its hull? The engine is silent, yet the ship keeps moving, because hundreds of thousands of tons cannot stop instantly. Inside the engine, fuel injection stops, combustion disappears, and the enormous crankshaft begins losing rotational energy. The crankshaft can no longer deliver torque through the shaft, so propulsion begins disappearing completely.
Now the storm's forces begin dominating the ship's motion, because continuous propulsive thrust has vanished.
Without propulsion maintaining heading, waves and wind can gradually rotate the vessel away from its original course.
The crew still has one critical tool, the rudder, which can generate turning force if water continues flowing across it. But as the ship slows, less water reaches the rudder, reducing its ability to change the vessel's heading.
On the bridge, alarms warn the crew that propulsion has been lost, and the vessel is drifting from its planned heading.
As the vessel turns more sideways, waves strike a larger area of the hull and increase rolling forces.
The navigation system now shows the crucial problem. The ship's actual motion no longer matches its intended course. The ship resists sudden changes because its huge mass creates enormous rotational and translational inertia.
The ship's enormous superstructure acts like a giant sail, allowing strong winds to create additional sideways force.
Meanwhile, the underwater hull resists sideways motion, creating a complicated balance of forces beneath the surface.
Meanwhile, the underwater hull resists sideways motion, creating a complicated balance of forces beneath the surface. Propulsion does more than move the ship forward. It continuously supplies the hydrodynamic control needed to maintain predictable motion. Engineers now inspect the failure, because restoring propulsion is the fastest way to regain control. Not every system fails with the engine. Cooling pumps and auxiliary equipment may continue operating independently. Lubrication is equally important because engineers may need the engine ready for restart without damaging bearings or moving components. The longer the engine remains stopped, the more the ship loses the thrust that normally stabilizes its motion.
Water resistance steadily removes the ship's kinetic energy, causing its forward speed to fall even though the hull remains intact.
Each wave transfers energy into the hull, creating repeated cycles of pitch, roll, and vertical acceleration.
Repeated wave impacts create changing stresses through the hull, especially when the ship encounters waves at unfavorable angles. If control becomes insufficient, the crew may prepare anchors, but deploying them safely depends heavily on depth, weather, and position.
The bridge also alerts nearby vessels and authorities, because a drifting ship can become a collision or grounding hazard.
With thrust still absent, the vessel's drift becomes increasingly determined by the changing relationship between wind, waves, and current. Unlike wind, ocean current acts on the submerged hull, quietly shifting the ship even when surface conditions look similar. The physics is simple. With engine torque at zero, the propeller produces no meaningful continuous thrust. Despite losing propulsion, the hull remains buoyant because buoyancy depends on displaced water, not engine power.
Now the ship's forward motion becomes weaker, while sideways drift increasingly determines where the vessel actually travels.
A ship can point one direction while actually moving another, especially when strong wind and current act on its hull.
The stronger the wind becomes, the more force acts against the ship's exposed superstructure above the water.
Below the surface, the underwater hull resists that sideways motion, creating an opposing hydrodynamic force. When these forces act at different points, they create a turning moment that gradually rotates the ship. The crew counters that yaw by turning the rudder, but its effect is now much weaker than during powered travel. As forward speed falls further, steering authority decreases, making precise heading control increasingly difficult. Then another large wave approaches from the side, threatening to increase the vessel's roll and yaw simultaneously. The wave hits the hull, transferring energy that briefly increases rolling and sideways acceleration. After the impact, gravity and buoyancy push the vessel back toward equilibrium, preventing the roll from increasing indefinitely. A large ship does not simply tip over, because its hull and weight distribution create restoring forces after moderate rolling.
The real concern comes when repeated waves interact with the ship's natural rolling behavior in an unfavorable rhythm.
Properly secured containers should not simply fly away. Failure requires forces exceeding their designed securing capacity. Even when the hull remains safe, repeated rolling places increasing loads on container securing equipment and deck structures. If engineers identify and correct the failure, restarting the engine could gradually restore propulsion and steering authority. Before restarting a giant marine diesel, lubrication and other required conditions must be established to protect its moving components. Fuel systems must also reach the required operating conditions before combustion can safely return. Once critical conditions are satisfied, the crew can issue a controlled engine start command rather than simply forcing the engine to run. Starting energy turns the crankshaft, bringing the engine back toward the rotational speed required for controlled combustion. Fuel injection resumes, controlled combustion returns, and individual cylinders begin producing torque again. As more cylinders contribute torque, the crankshaft accelerates and the propulsion system begins recovering useful mechanical power.
Mechanical torque now travels through the shaft, finally reaching the propeller at the stern.
The propeller begins rotating again, creating increasing water acceleration and gradually restoring thrust. Now the propeller generates forward thrust again, slowly reducing the ship's drift and improving directional control. As speed returns, water flow over the rudder increases, restoring much stronger steering authority. The crew now uses restored steering and propulsion to gradually bring the ship back toward a safer heading. Restarting the engine does not end the storm. It simply gives the crew back the mechanical control they were missing. With propulsion restored, the ship can better control speed, heading, rudder effectiveness, and its response to incoming waves.
The key lesson is that losing an engine does not remove buoyancy. It removes a crucial source of controllable momentum.
The storm was never the only threat. The real danger came from losing the ability to control how the ship responded to it.
The crew does not immediately apply full power. Thrust increases gradually to avoid adding excessive stress in the rough sea.
Inside the engine room, rising torque increases mechanical loads across the crankshaft, bearings, shaft line, and propeller.
As combustion increases, exhaust temperature rises, carrying more heat away from the cylinders through the exhaust system.
Meanwhile, the cooling system removes combustion heat, preventing the engine from overheating as power gradually returns. Lubricating oil continues circulating through bearings and moving surfaces, reducing friction as rotational speed increases. More engine power means more propeller torque, but the surrounding seawater pushes back against every rotating blade. At excessive loading, low-pressure regions can form around blades, potentially causing cavitation and damaging vibration. The crew avoids that risk by keeping power controlled rather than demanding maximum thrust from a recently restarted engine.
Forward speed slowly returns, giving the rudder enough water flow to produce meaningful steering force again.
Now the rudder can redirect faster-moving water, generating a stronger turning moment around the vessel. The vessel begins stabilizing its heading, reducing the dangerous sideways angle created while propulsion was unavailable.
A powerful wave reaches the bow, but forward motion now helps the hull respond more predictably to the impact.
The bow rises, the stern settles slightly, and gravity then pulls the vessel back toward its normal trim. Continuous thrust also prevents the ship from becoming completely passive between waves, improving its ability to maintain a controlled heading. On the bridge, officers monitor heading, speed, engine parameters, wind, wave conditions, and navigation data simultaneously.
Radar helps maintain situational awareness while the crew manages the vessel's position against the surrounding storm.
Wind sensors provide another critical input, because changing wind direction can alter the vessel's drift and turning behavior.
The actual path becomes the combined result of engine thrust, wind, current, waves, drag, and rudder forces.
By balancing those forces, the crew can choose a heading that reduces the most dangerous interaction with the waves.
Even with the engine running, ocean current continues pushing the ship independently of its own propulsion.
But if the storm intensifies again, the restored engine does not make the vessel invulnerable.
Larger waves increase resistance, forcing the propulsion system to work harder to maintain speed. The crew adjusts power carefully, avoiding unnecessary overload while preserving enough thrust for control.
The ship climbs another wave under controlled power, converting engine torque into forward momentum against gravity and water resistance.
As the bow descends, gravity accelerates the vessel downward, while water resistance dissipates part of that energy. Repeated wave impacts create cyclic structural loads, which engineers design the hull and internal framing to withstand. The engine restart improves control, but it cannot cancel wave energy, wind force, or the ship's own inertia.
Survival depends on managing these competing forces continuously, not simply turning the engine back on.
When propulsion disappears, the ship becomes largely a passenger of the environment. When propulsion returns, control begins returning with it.
So what really happens when a ship's engine stops in a storm? The answer depends on physics, redundancy, and time.
After restarting, engineers watch the engine closely because stability matters more than immediately restoring maximum propulsion. Stable oil pressure confirms that lubrication is reaching critical bearings and moving components throughout the engine.
Cooling temperatures remain controlled, proving the restarted engine is successfully removing combustion heat. Fuel delivery also remains controlled, supplying only the amount needed for the current propulsion demand.
Inside each cylinder, controlled fuel injection produces combustion, expanding gases that push pistons downward and create crankshaft torque. That torque travels from the crankshaft through the coupling and propulsion shaft toward the propeller. Intermediate shaft bearings support the rotating shaft, preventing excessive deflection as the propeller pushes against the water.
At the stern, the propeller converts rotational energy into a continuous stream of accelerated seawater, producing forward thrust.
The rudder now receives steady propeller flow, allowing hydraulic steering to control the ship more effectively. A small rudder adjustment changes the vessel's heading gradually, rather than forcing an immediate turn.
Because of its enormous mass, the 300-meter vessel needs significant distance to complete even a controlled change of heading.
Even after the rudder moves, the ship's momentum keeps carrying its massive hull forward before the new heading fully develops.
Strong crosswinds can still push the exposed container stacks sideways, creating additional steering demands.
Those stacked containers behave like a large aerodynamic surface, increasing wind drag across the vessel's exposed upper structure.
Below the surface, the hull experiences hydrodynamic resistance that opposes motion and grows with increasing speed. Every major wave transfers energy into the hull, producing motion that the ship's structure must absorb and distribute.
Despite the violent sea, buoyancy continuously acts upward, balancing the ship's enormous weight and keeping the intact hull afloat. Because the hull remains watertight, the storm does not automatically cause flooding simply because propulsion was lost. The electrical system remains active, powering navigation, communications, monitoring equipment, pumps, steering controls, and emergency systems.
Communication systems allow the crew to report the situation and coordinate with shore authorities or nearby vessels if required.
Visibility can become the next major problem, even after mechanical propulsion has been successfully restored. The bow continues meeting waves at an angle chosen to reduce dangerous rolling and excessive sideways forces. Keeping the ship from turning broadside reduces the risk of excessive rolling caused by powerful beam waves. Container securing systems now matter enormously because violent rolling can create dangerous loads on stacked cargo. With propulsion restored and heading controlled, the vessel's motion gradually becomes more predictable between successive waves.
Forward movement also increases the crew's ability to move away from hazardous areas, rather than drifting wherever wind and current carry them.
The longer propulsion remains unavailable, the farther wind and current can move a disabled ship from its intended route. The critical lesson is simple. An engine failure does not instantly sink a ship, but it can remove crucial control.
Once propulsion returns, thrust, rudder flow, navigation, and crew decisions combine to restore controlled movement through the storm.
With the vessel stable, engineers can gradually increase propulsion instead of demanding maximum power immediately.
As fuel demand rises, the turbocharger accelerates, forcing more air into the cylinders for efficient combustion.
More air allows the engine to burn additional fuel efficiently, increasing torque without creating excessive smoke or thermal stress.
Hot exhaust gases leave the cylinders, powering the turbocharger before flowing through the ship's exhaust system.
As power increases, combustion heat rises too, so the cooling system must remove additional thermal energy continuously. More engine torque reaches the propeller, increasing its rotational speed and strengthening the accelerated water stream behind the ship.
The stronger propeller slipstream produces greater thrust, gradually increasing the vessel's forward acceleration.
As speed increases, the bow creates a stronger wave system, requiring additional energy simply to push water aside.
Higher propeller flow also gives the rudder stronger steering authority, improving directional control in the rough water. The crew now has more propulsion authority, making small heading corrections without fighting the storm entirely.
The storm still dominates the environment, but restored propulsion now lets the crew actively manage the vessel's trajectory.
After the wave impact, engine load stabilizes, allowing propulsion to remain steady without forcing the machinery beyond safe operating limits.
Stable oil pressure keeps bearings, pistons, and the crankshaft separated by a protective film of lubricant.
The fuel system now delivers a controlled quantity to each cylinder, matching the engine's steady propulsion demand. Meanwhile, the ship's electrical network continues powering navigation, steering, communications, pumps, and essential safety equipment. Radar continues tracking surrounding waves and nearby objects, giving the bridge critical information while visibility remains poor. Instead of fighting every wave, the crew makes a small heading correction to reduce the vessel's exposure to the strongest impacts. The adjusted heading changes how waves strike the hull, reducing excessive rolling and improving the ship's overall stability. For the first time, a brief gap appears between the largest waves, giving the vessel a temporary reduction in external loading. The crew avoids unnecessary speed, balancing enough propulsion for control while limiting the loads caused by excessive acceleration. Now the ship reaches a controlled balance. Engine thrust pushes forward while wind, waves, and hull resistance push against it. Deep inside the hull, the propulsion shaft remains aligned and continuously transfers engine torque toward the propeller. Hydraulic pressure moves the rudder precisely, allowing small corrections while the propeller continues supplying strong directional water flow.
With propulsion restored, the ship is no longer drifting helplessly. It can now generate controlled forward motion and maintain a navigable heading.
The original engine failure has become a controlled emergency because propulsion, steering, cooling, and electrical systems are functioning again. If a ship's engine stops in a storm, it loses thrust and steering authority. Restoring propulsion is what turns drift into controlled survival.